In this lecture video, we will continue on the discussion about computer architecture. So we previously went through some of the fundamentals about the computer architecture, and now we will look briefly at a few of the real-world practicalities or compromises, if you will. We will also touch on some more operating principles, such as how does the CPU load program code, and how does different peripherals, that is input and output devices, connect to the processing unit. Let's start by looking at the computer architecture concepts. So we will start by reviewing some concepts from previous times, and then we will be introducing a few more theory concepts as well. So as you remember from last time, the all-encompassing idea of a microcomputer is what is called the programmable computer, which in turn is realized by the von Neumann architecture. So the central idea being that the central memory contains both executable instructions and the data they operate on. These programming instructions form what we know as software, of course. And this way, one processor is able to execute many different programs. If software is just code in the microcomputer's memory, it follows that by changing the program code, we can change what the computer does. Of course, moving program code from the computer's memory to the CPU and the ALU, arithmetic logic unit, requires quite a lot of scaffolding. That is what all the different buses in this picture are for. So the control buses, address buses, and data buses. As for transferring the instructions or program code from the memory to the CPU, well, this can be described as a repeated loop. The CPU fetches an instruction of exactly one word in length from the memory. Remember, the computer operates on a certain word length, a certain bit size, 64 bits, and in modern computers, 32 in older computers, and in our hack training platform, 16 bits. Then this instruction gets decoded, executed, and finally the CPU fetches what is the next instruction. Executing instructions may involve a couple of smaller steps. The ALU could compute some values, manipulate some internal registers, read some data from the memory, or write some data to the memory. And while the CPU is performing these tasks, it also figures out what instruction to fetch and execute next. So remember that this instruction can also alter the order of execution. So basically, if we need to, for example, if we have a conditional statement somewhere, we need to skip certain instructions in the code, or maybe we are inside a loop, then we need to repeat some instructions. So we may need to jump back and forth in the program code. The instruction to be fetched is normally stored in a special register that is called the program counter, or PC for short. And PC is just one general register. The registers, small memory slots, the size of exactly one word, are located near the ALU, and they can hold data or data addresses or addresses to instructions in the memory. Illustrated, this fetch execute cycle is not a very complex concept. Basically, all the control electronics that are tied to the CPU and the ALU, all they need to do is fetch some instruction from the memory, pass it to the ALU, which then executes it. And then we basically repeat the same process for all the instructions that in the memory. And once we run out of instructions, that is once we reach the end of the program, we simply stop. The difficult part of this very simple loop is doing all of the extra tasks that come with executing, fetching and executing instructions. So first, we also have to keep track of which instruction in the memory we are right now processing. So we also need to store the next instruction, the instruction that the CPU needs to fetch on the next cycle in some register for the memory address input. So basically the memory needs to take in some value which signifies which memory address needs to be read, and then as an output we get an instruction. And at the same time we need to update the bookmark of where we are reading instructions. And as mentioned before, this bookmark, or this where we are, which point are we at reading these instructions, is called the program counter. So we need to update the current address in the program counter on the same go. Executing the instruction basically for the ALU means decoding, figuring out what to do with the code. So basically, which arithmetic or logical instruction is this piece of binary data? On what memory addresses do those operations need to be applied for? So for example, different subsets of the instruction bits control different aspects of the operation. Consequently, we need to figure out what to do after processing this one instruction. So there are instructions in machine code called conditional jumps. So depending on some arithmetic operation, we might have to jump to a different location in the source code or in the machine code. Executing the instructions basically involve accessing, so writing and reading from registers, and or at sometimes accessing the data memory, so the data in the memory. Still, even taking into account these little remarks, this fetch execute cycle still not a very complex concept. There is one problem though. As you remember, the memory contains both program instructions and data. So when we read something from the memory, in this fetch execute cycle, we are only talking about passing values from the memory here to the ALU to be executed. The problem in this is that not everything in the memory is program instructions. They could also be data. So what happens when we need to move data to be processed at the ALU? So the problem illustrated here is if we have both data and program code in the memory, but we only have one process in which we load details or from the memory, then effectively we only have one output. Similarly, to control which parts of the memory we should transfer to the ALU, we only have one input, so we do not have different data buses for the instructions and the data. So what we see here is what is called a fetch execute clash. So if the memory is only one address space, which in modern computers it actually is, this fetch execute scheme will not work because we only have one memory input and one memory output, yet we have we have the need for two outputs and two inputs, one input and output for data and one input and output for program instructions. Of course, unsolved, this problem would render the von Neumann machine unusable, but as we have stated, the von Neumann machine is a blueprint for all modern computers, so there must be some good solution to this problem. And there are actually two good solutions. The first one is presented here, so it involves solving this data instruction clash by using a multiplexer circuit and an instruction register. So if we start from the instruction register, it sits on the bus from the memory toward the ALU, so from left to right. And it connects the data bus on the top to the control bus on the bottom. The instruction register basically holds the memory address for whatever is the next instruction to be executed. And then this address is passed through the control bus, the bus that is dedicated for transmitting addresses of instructions in the memory. The address of the instruction also carries something called a fetch execute bit. So this is a 1-bit flag that determines whether the line of code at that address is indeed an instruction or other binary data. The fetch execute bit also controls another component, the multiplexer, or MUX for short. If you remember from Boolean arithmetic and logic gates, a multiplexer is a selection device that, given a value of a control bit, selects between two inputs. So this fetch execute bit that comes from the instruction register is used to select between inputs from the control bus and the input from the address bus. And again here, the control bus contains instruction addresses that point to lines of program code or machine code, and addresses of data addresses in the address bus. So now, depending on which bit is flipped in the fetch execute flag, the multiplexer knows how to handle the memory inputs correctly. So whether to read or write some data to the memory, or whether to fetch a program instruction from the memory. Meanwhile, on the right, the program instructions flow to the ALU via the control bus, and the instruction register is updated to fetch a new instruction if we need to move on to the next operation in the program. The multiplexer and instruction register is a practical and very fast and the more commonly used solution to the problem. There is another simpler solution, which is basically separate the memory units, separate data and program instruction memory units. This is actually used in some simpler microcontrollers. So all modern CPUs probably use the instruction register and multiplexer combo, but sometimes you see microcontrollers that have separate memory units. And this approach is called sometimes called the Harvard architecture, which is a variant of the von Neumann architecture. And this is also the way the virtual hack computer is organized. So the hack actually has separate memory units, one for program code and one for data memory. So the idea simply is there are two physically separate memory units, some memory reserved for data, instruction data, and some for program data. And each of these memory units can be addressed and manipulated separately and also at the same time. The advantage of these is that the instruction register and multiplexer approach is slightly complicated, and separating the memory units is much simpler. It does come with disadvantages though. So now we have to fit 2 memory chips into this architecture instead of 1, and also the size of both memory chips is fixed because we need approximately the same size of memory for instructions as we do with other program data. Something else to keep in mind, the CPU and the memory units are not the only physical components of a computer system. We also need input-output devices to communicate with the CPU. So those include screens, keyboards, printers, scanners, network interface cards, CD, DVD, ROMs, or Blu-ray players, whatever there are. Also, since we nowadays fit computers to every single thing in the world, there's a bewildering array of different components that embedded computers have. For example, things to control in cars, or weapon systems, or medical equipment, and so on. Usually we do not talk about input-output devices a lot, and there are a couple of reasons why we don't do that. Well, first, each and every one of these different peripheral devices represents some unique piece of machinery that requires a lot of detailed knowledge about how it has been built and engineered. Secondly, for the same reason, or for this very reason, in computer science, we have actually figured out a way to make all of these different input-output devices, all of these peripheral devices, to look exactly the same to the computer or to the CPU. And we will look at one of these approaches, which is called a memory mapped input-output. So the basic idea of memory mapped I/O is to create a virtual device that is basically a binary emulation of whatever device you are using, and making it look to the CPU like some particular memory segment. So basically each I/O device is allocated some exclusive area in the memory, which becomes what is called its memory map. And for each input device, this memory map is made to continuously reflect on the physical state of the device. So when some external event happens on an input or output device, for example on your keyboard, that external event could be pressing a key, or for your mouse it could be moving the mouse, or for the screen when something is drawn on the screen. From a hardware point of view, we need some I/O device to provide an interface that is similar to that of a memory unit. And from a software point of view, each I/O device is required to define an interaction contract so that programs can access them correctly. In practice, what most I/O devices do is they come with either a software or hardware control unit, or in software terms, often this is called a driver. And this control unit or driver will then write the necessary bits into the memory segment of each device. And given how many different computer platforms and I/O devices there are, memory mapped I/O makes a lot of sense. So the design of the CPU and the whole computer architecture can be totally independent of the number and type or nature of the I/O devices that interact with the computer. So whenever we want to plug in a new I/O device, all we have to do is allocate it to a new memory map, take note of this memory maps base address, and from then on, all we have to do is basically have this controller manipulate these bits in the memory according to what the I/O device is doing. Finally, what do I need to remember from this lecture? So keep in mind the big picture still. How are we making computer programs work? How does high-level code actually turn into something that can be executed by a CPU? We looked at the computer architecture and some of those theory concepts to understand better how the computer works. We looked at the fetch execute model and some of its problems.